This is P4G7, Karmen Pang 4.20.
Victoria Wittenbrock 4.32.
Destiny Duran-Gonzales 4.7.
So I'm number 4, so I will start with neuron anatomy. So this is the presynaptic neuron and this is the postsynaptic neuron. And these projections up here are the dendrites, and they receive the transmission from the previous neuron. And they receive the impulse and send it to the soma where it's processed, which is the body of the neuron. And then it's transmitted down the axon to the axon terminal. And the action potential is then sent across the synapse to the postsynaptic neuron, and then it's received by the dendrites and processed by the soma, and the process is continued.
And if we were to zoom in at the synapse, we would see the structure over here.
So I have number 2, I'm doing synaptic transmission, and the calcium channels open on the presynaptic axon terminals, which allows calcium to flow in, and it causes synaptic vesicles to fuse with the axonal membrane, and calcium is either absorbed by the mitochondria or ejected by calcium pumps. And since the synaptic vesicles and axonal membrane fused, it releases a neurotransmitter that binds to the receptors on the postsynaptic neuron.
So when neurotransmitters or ligands bind to receptors on the membrane, this is when depolarization begins. So at this point where the orange type thing is. So when the ligand binds to sodium ligand-gated channels, there's a sodium influx, meaning that sodium has entered the cell, and this alters the membrane potential from -70 to -55 millivolts. And at -55 millivolts, the sodium voltage-gated channels open. And this causes more sodium to enter the cell, which makes the membrane even less negative, reaching up to positive 30 or 35 millivolts. And when this happens, at -55 millivolts, at 30 or positive 35 millivolts, the sodium-gated channels begin to close, and the potassium-gated, voltage-gated channels start to open. So when this happens, there's a potassium efflux, meaning that potassium has left the cell, has traveled across the cell membrane to the outside, and this causes the membrane potential to become -70 again, but the potassium voltage-gated channels are slow to close.
Okay. So because the potassium voltage-gated channel lacks a subunit, it takes longer to close, which results in an excess of potassium efflux, which means that the membrane goes beyond its resting point of -70 millivolts, and it reaches -80 or 90 millivolts, and that's known as hyperpolarization. And that occurs on this period in the graph where it passes its resting membrane potential of -70, and it goes past that here in this pink area. That's hyperpolarization. So eventually the gates close, and then that's when the sodium potassium pump works through active transport. Yes, through active transport, and it pushes the potassium and the sodium back in a 3:2 ratio so that it can reach its resting conditions again.
So the resting conditions would be that there is more sodium on the outside of the cell compared to the inside, whereas there's more potassium on the inside of the cell than there is on the outside.
And another resting membrane condition is that it's charged and it's polarized, which means that it has more negativity on the inside than on the outside of the cell.
And the resting membrane potential when the cell is polarized would be at -70 millivolts.
And like we said earlier, the sodium-potassium pumps require energy to reestablish the resting membrane conditions. So there's the all or nothing phenomenon, which states that if the stimulus isn't strong enough, then no action potential will be sent.
And this is the absolute refractory period, which occurs
At the beginning where synaptic transmission begins to the middle of repolarization, and then
there's the relative refractory period.
where it needs an exceptionally strong stimulus in order for another action potential to be sent.
and then during the absolute refractory period, even if the stimulus is exceptionally strong, it still won't be sent.
Yeah.
Mercy is the best policy.
Wait, did I mention the threshold? Okay, at negative 55 millivolts over here, there's a threshold, and if that is not met, then the sodium voltage-gated channels won't open. So the membrane will return to negative 70 millivolts.